We had left lecture 2 asking ourselves some questions. Why for zeta equal to 1, zeta equal to zero point 0.1, the response was fast. If you see it, is the first. So this is the desired step. This is a desired reference. It's 1, and you want the system to reach the point 1 and stay there. 1 is the blue line is the one to reach the first, which with zeta equal to 0.1. But well, it goes all the way till 1.7, again comes back, goes back all the way till somewhere between minus 0.45, and so on and so forth. As I keep now look at, say, some other zeta, say zeta equal to 0.5, which is the green line. The green line, well, it reaches 1 much later. But the good thing is it doesn't go all the way till 1.7. It maybe stops somewhere around 1.15 or something like that. Even in the negative, it goes just to maybe 0.95 and so on. So we have two things here, right? So this is the response here is fast, but it really goes very far away. The response here is slow, but that's okay. It doesn't really go very far away. Say, for example, I'm looking at currents, right? Maybe I want to stabilize to a current of 5 amperes. I don't want the system to go to 10 amperes and come back to 3 and then slowly settle down, because my equipment may have some current rating or some voltage rating or any of those which may cause damage to the system. Okay, so we had left lecture to answer asking few of these questions. So why does this happen? Okay, hello and welcome to lecture 3. Uh, in this, we will try to answer some of those questions which we had left unanswered in lecture number 2. Okay, now we talked about how fast the response was. The faster the response, essentially, I was interested in those plots between for zeta being between 0 and 1. For point zeta equal to 0.1, the system really went very far away from what was desired. It went till 1 point. It went faster, but it had a lot of overshoot. So how does this affect the performance of a system? Which kind of zeta should I choose? Should I choose a zeta which is between 0 and 1? Should I choose a zeta which is greater than 1 or much greater than 1? So performance specifications for a control system, especially in the design, often involve requirements associated with the time response of the system. Response could be what would be a typical human tendency? If I switch on my AC and I want it to go till 24 or 21 or whatever is my comfort level, or even if I go get into my car on a hot day outside, as an end user, I would want the design to make to cool down my room or cool down my car almost instantaneously. Okay, which means the response must be faster. What we saw in those plots was if the response was faster, it had an overshoot. It had to go till 1, but it was going till 1.7, 1.8, falling back, and so on and so forth. Okay, so this gives us a little insight into what could design specifications be. In particular with respect to step changes or any other transient conditions. So we'll see how this rise time or how fast the system responds is a good measure of how to design the system, or including overshoot. And there'll also be something like how fast the system settles down to its steady state value, or even after a disturbance and so on. So this will be the motivation for this lecture, to understand specifically those plots which varied as zeta varied from 0.1 till 0.9. Okay, so let's quantify a few things. We saw that the line which had zeta equal to 0.1 was the fastest to move. Until the zeta equal to 0.5 was slower, until 0.9 was the slowest in that batch. Okay, we'll see some of these definitions now. So we'll talk of the rise time, which is the time it takes the system to reach near the vicinity of its new set point. Settling time, how fast the transients decay, how fast does it go to the desired value. We'll have overshoot largely, which was defined as how far away it goes from one after it reaches it first. And then the peak time is the time that it takes to reach the maximum overshoot. Okay, let us try to understand those quantities through a step response. The system should reach this set point of 1. It could be 10 or 20, but for ease of explanation, I am using this number 1. The system is fast to move. Let's say I'm at zeta equal to zero point 0.1. The system moves very fast. But what I see is when the system reaches fast, it actually overshoots. Right? If I'm really running fast to meet a target, I might actually go further than the target, right? Because I just cannot stop at 1, loosely speaking. Okay, so there will be the system reaches 1. What is the first instance that it reaches 1? I can calculate this from as a time from here till here. Then the system reaches some peak. Once it reaches this peak, the second peak is smaller than this, and third peak is smaller and much smaller, and so on. Okay, so this I will call this as the peak overshoot, the corresponding time as the peak time, and I will allow a little bit of tolerance to see when I have settled down. For example, I want to go to a temperature of 24. I'm okay if I'm like at say a temperature of 24.2. It doesn't make me feel very warm, or 23.8 doesn't make me feel much colder, right? So there'll be some tolerance level where I can design my system to be. I don't really, even if I'm going at a speed of 60, 60.2 or 61 or 59 doesn't feel extremely fast or extremely slow respectively. So how do we keep this in mind while designing a system, and how do we even quantify this? Because everything we should be able to relate to a system property. Okay, so how do we quantify the rise time? So if I look at an overdamped system, I didn't really explicitly plot it here, but okay, let me look at a green clear. But if I have an overdamped system, it will have no overshoot for an overdamped system. That again comes from the way we had seen the solutions of our equations. Okay, so how do I define these things? So for an overdamped system, I look at the rise time as the time required for the system to go from 10% to 90% of its final value. So if I'm going from 0 to 1, I would look at the rise time as a time required to go from zero point 0.1 to 0.9. Whereas for an underdamped system, I actually reach 100% of the value and then I overshoot. So I can quantify this very nicely as a time required to reach from 0 to 100, 0 to 100% of the final value at the first instance. So there are several instances where it crosses that method. This is the first instance, this is the second instance, third instance, and so on. But I'm interested in the first instance. Okay, so I know how the solution to this system looks like. I just equate the right hand side to be equal to 1. Okay, and then I can just do a little math to find. Okay, I'll skip these calculations. These are kind of pretty straightforward. So this is what you can see, right? That the rise time depends largely on the system properties, on the zeta and the omega n, right? So therefore, for different zeta, we had different rise times. So the system reached faster or slower to the point 1. If you see that the blue line with point 1 was faster than the green line. If I just go back to the value of zeta. So this is the rise time. Sorry. So this was the rise time here from here till here. Green one was a little slower, and so on and so forth, where we go till the slowest one, maybe possibly being the red line at point 0.9. So we have a different rise time, and a different rise time is depending on the value of zeta. Okay, This is nice. So it gives me some indication of how fast or how slow my system is. Okay, so again I get this plus. So in an underdamped system, the larger the value of zeta, larger is the rise time. Or lesser zeta, faster is my system response. So lesser the zeta, faster is my response. So if I were to say I want to my room to go to 24 degrees, so let's say it starts off at 40 and this is my 24. Faster response might go to 24 first, it might go till 18 and then it might go and so on and so forth. Am I okay with my room temperature going till 18 before it settles down at 24? Or would I be okay to wait for a little longer until it goes until it goes to its desired temperature of 24 degrees? That just as a user, I can design my comfort levels, or even based on some practical considerations, should I want the system to be over damped or under damped? Here I'm still okay if the temperature goes till 21 or even 22. If I design a lift, right, I really don't want the lift I want it maybe to go from 0 to the fifth floor. Would I design it to be over damped or under damped? I don't want the lift to first overshoot till the seventh floor, again go back to the fourth floor and slowly settle down. I would want that system to be like an under damped system. Right? I don't want an overshoot. So there are systems which overshoots are allowed. There are some systems which I wouldn't want overshoots to happen. That really depends on the design specifications. Okay, the next quantity that we will define is the delay time is the time required for the response to reach 50% of the final value. So I'm just looking at, so this is the steady state value of one. I'm just looking at what times does this things reach. Again, you see it has a very nice dependency on the value of zeta. Again, in underdamped systems, the larger the value of zeta, larger is the delay time. Okay, peak time. How do we quantify this? So at peak, I'm just looking at, now I'll go back to ask calculus few questions. Peak time, this is the maximum value. Calculus teaches me that just differentiate the function, set it to 0 and calculate the corresponding values. So the peak time, again, I'll skip these steps. These are beautifully explained here. We'll just try to understand what this means. The peak time also now has a nice dependency on zeta. Okay, now what is the value of y at TP? We were interested in how much is this overshoot? Why does this go till 1.7? Why does this go till 1.35? Why does this not go beyond 1.2? Okay, just calculate. So these are the different peak times and they keep on increasing. At peak time, what is the value? Well, this kind of turns out to be a nice expression now. So the peak overshoot we'll now define in terms of percentage of the steady state value. The normalized difference between the peak value of the response time and the steady state time. So I compute the value at the peak. This I know. This is the time which I just computed. I know what the steady state value. If I'm just looking at a step signal, my steady state value is 1. I do all the math and I get some number like this. The peak overshoot has a very nice dependency only on zeta. Okay, e power minus zeta pi over square root of 1 minus zeta square. It depends only on this value of zeta, and therefore you see that as the value of zeta changes, my overshoot drops. Keeps on dropping. Even though as the things drop, my rise time, even though it increases. Okay, so what is therefore the relation between zeta and the percentage overshoot? We'll measure this in percentage. For zeta equal to 0, I will have a 100% overshoot just from the formula. And we also see it in one of those plots where why does the plot go from I think let me figure out where that was. This here, right? Zeta equal to 0 and I reached a value of 2. So desired was 1, peak goes to 2, which means 100% overshoot is again for zeta equal to 0. Maximum overshoot for the system without any damping. And it keeps on decreasing as the value of zeta increases. So you see a very nice relation now between the damping ratio and the peak overshoot. So typical frequently used values are peak overshoot of 16% for zeta equal to zero point 0.5 and a peak overshoot of 0.05 for zeta equal to 2.69 and so on. These are possibly allowable values of overshoot. So we largely look at a damping ratio which is around zero point 0.5 or between zero point 0.5 and zero point 0.7 so that our overshoot doesn't be too large. Now settling time. How fast does my system settle down? Settle down essentially means that I am now looking at this part of the graph. I'm okay with the transients are dying down, but okay, now I just want to really settle down to some point here, maybe between 24.2 and 23.8 degrees. We need to mathematically quantify even this. So I define now my settling time as a time required to reach the steady state value and stay within that perfect tolerance band, maybe plus minus zero point 0.2 degrees. I can define it based on my design specification. Mathematically, I can quantify this as two things as a 2% tolerance. So if it's say 100, I am allowed to go between 98 and 102. 5% tolerance, if the steady state, the desired is 100, I'm allowed to go between 95 and 105. And we see that settling time is inversely proportional to the damping ratio, that as the zeta increases, TSG decreases. So let's look at this. What happens when zeta equal to 0? Zeta equal to 0, I'm just oscillating, right, all the time. You say the system is oscillating, so it will never reach steady state. I mean, this is the steady state, right? So as zeta increases, settling time decreases, or as zeta decreases, settling time increases. In the limiting case, zeta equal to 0, the system never settles. Or the settling time is infinity when zeta equal to 0. You can see also mathematics, zeta equal to 0, settling time just becomes infinity. Okay, so the discussed specifications now characterize a transient response of a system having no finite zeros. Of course, we were not looking at zeros, and two complex poles with negative real parts and with undamped natural frequency zeta and omega n. Zeta representing the damping ratio, omega representing the natural frequency. And this gives us a very nice way to estimate or calculate what are the rise time, overshoot, settling time. I will now know how fast or how slow my system will settle down. If a system was to settle faster, then is there a larger overshoot and so on. Now I can have a design problem which can kind of try to optimize or work around these quantities. Okay, so for specified values of, if somebody gives me, okay, I give you a specified rise time, I give you a peak overshoot, I give you a settling time, can you find the system which does that, right? I can then look at, okay, for if given an MP, given a peak overshoot, I can now neatly design what is my zeta. So I have omega n square plus s square plus 2 zeta omega ns plus omega n square. And I want to design a controller, or design my system, or design my damping appropriately. Given a MP, I can easily find zeta from this value. Okay, and similarly, I can also look for omega n. Okay, and these values, of course, are meant to provide a starting point for design iteration. We will emphasize a little more while we are doing while we solve actual design problems. Okay, a simple synthesis problem for you to solve. Find the allowable regions in the S-plane. So we had drawn our S-plane, we had marked our poles here, we had marked our angles and called this as sine inverse of something, cos inverse of something, and so on. Find the allowable regions in the S-plane for the poles of the transfer function if the specifications are such that the rise time is less than zero point 0.6 seconds, overshoot is less than 10%, and the settling time of less than 3 seconds. Think about this. We'll try to answer this shortly. In this lecture, we have looked at several transient analysis specifications. We'll also look at what happens in the steady state in the coming lecture. Stay tuned. Thanks for listening.